Hello, Chem 201 Organickers. Today we're going to talk a little bit about another prerequisite general chemistry topic that's really important to organic chemistry. That is drawing Lewis dot structures. Regardless of which prerequisite course that you took, you should be pretty proficient at drawing Lewis dot structures. So we are going to go over some of the highlights of what you really need to know in order to succeed in this particular class. So let me connect to my iPad and go over a few slides with you. So again, regarding of which chemistry class that you took as a prerequisite for Chem 201, we will need to know how to construct Lewis dot structures according to the molecular formula for the molecule. There are many different bonding theories, and depending on the course that you took, you may know more theories such as molecular orbital theory or valence bond theory. All of you, regardless of which prerequisite class you took in order to enroll in Chem 201, need to know about bonding theories that are related to the Lewis model of bonding. So in general, when we consider bonding theories, this is how we explain how and why atoms attach together to form molecules. These theories explain why some combinations of atoms are stable and others aren't. For example, why is water H2O and not HO or H3O? And we can also use theories to predict the shapes of molecules. In organic chemistry, the shape of the molecule is going to be very critical. So we need to be able to draw Lewis structures of various organic molecules. These structures can also be used to predict the chemical and physical properties of compounds. As we are going to see, the actual three-dimensional structure of molecules has a lot to do with what type of physical properties compounds have. And as we learn about organic functional groups, we're going to relate all of this back to the type of structure that you get when you draw Lewis structures for these various organic molecules. So let's look at the Lewis model. This is one of the simplest bonding theories among all of the various bonding models. Lewis theory is going to emphasize the use of valence electrons to explain bonding. By using Lewis theory, we can draw a model which is called a Lewis structure. You may know these as electron dot structures. This gives us another level of information because when we draw a Lewis structure, we not only know which elements and how many elements are contained in the molecular formula, we also know which atoms are bonded to other atoms and sort of the nature of those bonds. Is it a single, a double, or a triple bond? Is it charged or is it uncharged? We can look at all kinds of information from Lewis structures, including we can look at molecular stability, shape, size, and polarity. Now, just as a review, there are three different types of bonds, and they include ionic bonds, which are between a metal and a nonmetal. Remember, the characteristic feature of this type of bonding is electrons are fully transferred from one element, usually a metal, to another element, usually a nonmetal. The metal loses electrons to form a positively charged cation. The nonmetal gains electrons to form a negatively charged anion. And the bond is actually that electrostatic attraction between oppositely charged particles. We've also, in your prerequisite class, discussed covalent bonding. This usually occurs between a nonmetal and a nonmetal. Here, the characteristic feature of a covalent bond is that electrons are shared. Covalent bonds can be grouped into two different types of bonds called polar and nonpolar, which we're going to talk about in a separate lecture. For now, we're going to focus on these two types of bonds, ionic bonds and especially covalent bonds. In organic compounds, carbon is the central element to all of the organic compounds that we're going to discuss. Carbon forms covalent bonds. So covalent bonding is the most important type of bond when we discuss organic chemistry. Metallic bonding is another type of bond, but we are not going to discuss that too much or at all in this particular class. Here's just another sort of visual about these type of bonds. When I have covalent bonding, I can involve nonmetal to nonmetal or nonmetal and metalloids. My electronic distribution is shared electrons between different atoms. So the picture here is bromine. This is Br2. It's a halogen. It's a diatomic molecular element. And this is what it looks like in the lab if you were to look at a various sample. This is sodium chloride. This is ionic. This is table salt, and you can see I have this lattice array of sodium positively charged cations and chloride negatively charged anions, sort of alternating in this solid lattice type structure. And then this is what it would look like if you ever paid attention to the salt that came out of your salt shaker and you looked at it really closely, maybe under a magnifying glass even, you would see that you get these crystalline objects as part of your salt. Again, we're really not worried about the metallic type of bond. We're going to definitely focus on this part in this class because, again, that is the prevailing mode of bonding for carbon. So let's just reiterate what a covalent bond is. Non-metal atoms have relatively high ionization energies. It's actually very difficult to remove electrons from them and form positively charged cations. So when nonmetals bond together, it is actually better in terms of potential energy for the atoms to share valence electrons instead of transfer them. And we know that potential energy is the lowest when the electrons are between the nuclei. So here, when these electrons are between the two positively charged nuclei in this bond, I have the lowest potential energy or the most stable configuration for this particular bond. Remember, valence bonds or valence electrons are held most loosely because they're in that outer energy level. Chemical bonding involves either the transfer or the sharing of electrons between two more atoms. Because of this, what we know is valence electrons are most important in bonding. So we have to be able to look at the valence electron configuration of atoms in order to draw Lewis dot structures. This is because Lewis theory actually focuses on the behavior of the valence electrons. We know that the column numbers on the periodic table will tell you how many valence electrons in a main group atom has. Now this is that main group, right? So this is 1A through 8A, the A elements, the S block and the P block, right? We're not looking at D or F electrons. We're only looking at the main group atom, which contains the S group or the S block and the P block. So if I have something in 1A, I have one valence electron. If I have something in group 7A, I have 7 valence electrons. Group 8A, again, is the noble gases. In a Lewis structure, we're going to represent those valence electrons of main group elements as dots, and those dots are going to surround the symbol for the element. So this is our electron dot structure. In order to draw a Lewis structure for a molecule, we start with the electron dot structure of a particular element that's engaged in bonding. So for example, oxygen, right, is in group 6A. It has 6 valence electrons, so it has 6 dots. 1, 2, 3, 4, 5, 6. Those dots are representing the valence electrons around the atom oxygen. Unpaired dots represent bonding capacity. So we're going to talk about this a little bit later, but recognize any element that is in the same column is going to have the same type of bonding capacity, the same type of bonding scheme that any other atom in that same column has as well. Remember, we're focusing on the main group elements, the representative elements, which means that the members of the same family or column are going to have the same number of valence electron and similar bonding capacities. As we get into row 3, 4, 5, and higher, we know that we can also do other things. Those are special forms of elements. We can form what's known as expanded octets there. But luckily, most of our bonding in terms of organic is in group 2, where we actually only have a capacity for 8 electrons around the atoms. Neon doesn't bond, but carbon, nitrogen, oxygen, and fluorine are used a lot. So we're going to focus on those and then just touch on expanded octets for when we get into elements that, you know, use these other, or molecules that use these other elements in terms of their structures. Now, atoms bond because bonding results in a more stable electron configuration. Remember, I want to be like a noble gas. If I'm more stable, I have a lower potential energy. So in order to get this stability, atoms will bond together by either transferring, in the case of ionic, or sharing, in the case of covalent, their electrons with one another. Usually this results in all atoms obtaining an outer shell with 8 electrons. This is called the octet rule. There are some exceptions to this rule. The key to remember is you want to try to get an electron configuration like a noble gas. So that's the prevailing principle for how we put these elements together in order to find a structure. So in the octet rule, main group elements will tend to undergo reactions that leave them with 8 outer shell electrons. That means they have NS2, NP6, right? 6 plus 2 is 8. The main group elements will react, so they attain a noble gas electron configuration, which include a filled S and P sublevel in a particular valence electron shell. When we talk about ions, right, metals will lose more electrons to become a positively charged cation. Nonmetals will tend to gain 1 or more electrons and become a negatively charged anion. It's the electrostatic interaction between those oppositely charged particles that form the bond. So if you recall, sodium has a valence configuration of 3s1, 1 valence electron group 1a. Chlorine has a valence shell electron configuration of 3s2, 3p6. Remember, I want to get to ns2 and p6. If I lose this one, I achieve a valence shell octet, even though it's in group 2 or row 2. If I add 1 electron, I end up becoming like a noble gas. Chlorine will add that 1 electron to fill that last space in its 3p subshell. What I end up is 3s2 3p6, which is a filled shell. So this is a filled shell, and this is a filled shell. Sodium lost it to become +1. Chlorine gained that electron to become -1. And those oppositely charged particles are now attracted to each other and form the ionic bond. So I can use Lewis symbols to represent the transfer of electrons. Here I have a metal, and here I have a non-metal. This wants to lose an electron. This wants to gain an electron. So here I lose this dot. This dot actually goes onto the chlorine. It'd be better if I drew it this way. This dot actually goes here to fill that outer, that spot to allow the chlorine to become a -1. Notice I have no dots here because the valence shell electron was lost, and I have 8 dots there because I had 7 valence shell electrons, but now I've added that 1 electron that potassium lost to form the Cl-1 ion. Ions are usually indicated in brackets. So when you see brackets in these different bonding schemes, most of the time when you have an ion, what you're doing is indicating that it is a charged species by putting the Lewis dot structure in brackets. Now, Lewis theory for covalent bonding involves sharing of electrons. Instead of transferring, I can achieve an octet by sharing electrons with other atoms. These shared electrons would then count towards each atom's octet. So basically, I'm going to double count those shared electrons. This model of forming a bond is called covalent bonding. Electrons that are shared by atoms are called bonding pairs. Those are the pairs that you're going to see that are actually in between 2 different atoms. And then electrons that are not shared, but they're actually localized on a particular atom is called a lone pair. So here this oxygen has 2 lone pairs. Those lone pairs are not engaged in bonding. So the hydrogen donated 1 electron, the other hydrogen atom donated 1 electron. Now if I count them, I have 1, 2, 3, 4, 5, 6, 7, 8 around oxygen. I just filled the octet around oxygen. I have 2 electrons that fill the duet in hydrogen, right? Hydrogen has a duet rule because to fill its shell, I go to 1s2, so I only have 2 electrons, and then it's like helium. So hydrogen is actually an exception to the octet rule. So we're going to use this octet rule in order to draw electron dot structures or Lewis structures. We're going to look at the formula. We're going to represent each atom in the formula's valence electrons by dots. And then we're going to indicate the placement of the dots in the way that those valence electrons form bonds and are thus distributed without the molecule. An example of this is a very simple molecule, which is H2. H2 is a diatomic molecular element. And it wants to have a duet because it wants to be like helium, right? I want to be like a noble gas. Each hydrogen atom has 1 valence electrons, right? So if I just put those one valence electron and I connect the dots, what I'm going to end up with is an electron pair that forms a bond between those two hydrogen atoms. That bond is now a covalent bond in the hydrogen molecule. So what I see on the bottom here is that this hydrogen is now bonded to the other hydrogen. Each one of those hydrogen atoms donates an electron to form this bonding pair and thus form the molecule. When two atoms share one pair of electrons, it's called a single covalent bond. But in organic chemistry, as in general chemistry, sometimes an atom has to use more than one single bond to fulfill its octet. So for example, I could have double and triple bonds that we're going to discuss in organic chemistry. Here, I'm looking at how I form water, right? If I look at the formula, I have 2 hydrogens and 1 oxygen, right? So I'm going to put my hydrogen down here, and my oxygen has 6 electrons, so I have 6 dots. And then my other hydrogen has 1. I'm basically just going to connect the dots. And when I do that, I end up with each hydrogen atom having a duet, and with the oxygen atom having an octet, because it's accepting each electron from each separate hydrogen atom to fulfill its octet and get 8 electrons around it. So I have bonding pairs that are forming the actual bonds, and then I have these lone pairs which are on oxygen, they're localized on oxygen, but they're not engaged in actual bonding. They're there because they fulfill the octet around the hydrogen. Here's another way that I could use this model in order to predict bonding. 2 fluorine atoms, right? Fluorine are in group 7A. I have 7 valence electrons around each one. All I want to do is connect the dots, and then I end up with this fluorine molecule. Fluorine is also a diatomic molecular element. We know that in nature, fluorine is found as F2, not as discrete fluorine atoms. Well, oxygen and nitrogen, these are also diatomic molecular elements. But in order for this to work, what I have to do is share 4 electrons in oxygen and 6 electrons in nitrogen, right? So this is a double bond indicated by 2 lines between the 2 oxygens. This is a triple bond indicated by 3 lines between the nitrogen. Each single bond is represented by 2 electrons. So if I have 4 electrons, I have a double bond, and if I have 6 electrons, I have a triple bond. There are no other electrons that I can add to these structures. Oxygen has 6 valence electrons and 6 valence electrons. That's a total of 12. I have to give everybody an octet by using those electrons. In order to give both oxygen atoms an octet, I end up sharing 4 electrons between the 2 oxygen atoms, which indicates that I have a double bond. Same thing with nitrogen. I have 5 electrons and 5 electrons. That equals 10 valence electrons. I have no other choice. I can't add or subtract electrons to make this work. In order to give each nitrogen an octet, I end up with a triple bond where I have 6 electrons actually shared between these nitrogens. So if I do that, if I look at this, this is going to have 2, 4, 6, 8, and then this nitrogen is going to have 2, 4, 6, 8. Everybody has an octet, everybody is happy. So that's what I'm looking for when I form these double and triple bonds using Lewis structures. So how do I draw these? I look at a formula and I figure out the total number of valence electrons that I'm using, which encompasses all the atoms in the molecular formula. I'm going to add one additional electron for each negative charge if I have an anion, or I'm going to subtract one additional electron for each positive charge if I have a cation. We're going to talk about that a little bit more when we talk about formal charges. But recognize that I can add electrons if I have a negative charge, and I subtract electrons if I have a positive charge when I'm drawing charged Lewis dot structures. I do a method which is basically called connect the dots. I'm going to place the element that has the highest bonding capacity in the center. I'm going to surround the central atom with the other elements in the formula. And I'm going to connect the dots to draw lines to represent bonds between atoms. To do this, I'm going to use the suggested normal bonding capacity guidelines to start. When I have charged molecules, these suggested normal bonding capacities will change. And we're going to talk about that also when we get into formal charge. So what are these normal bonding capacities? Let's go over a few elements. If I look at hydrogen, I have one electron, right? So this wants to form one bond. It is an exception to the octet rule because it wants to accept an electron to form a bond. So hydrogen is usually forming something like this to some other atom. This is going to be my duet, and usually this is a terminal bond, which means that it sort of fills space around different carbon atoms. You're going to see a lot of hydrogen surrounding carbon atoms when we get into organic chemistry. If I look at the next one, I have beryllium, which is in group 2 and has 2 valence electrons. Beryllium wants to form 2 bonds. It's an exception to the octet rule. It actually is going to form electron deficient species if it forms a covalent bond, and beryllium is going to look like this. So I might have BeCl2, where I'm going to have something that looks like this. And if this is a covalent bond, this is going to be a linear structure. We're going to talk about VSEPR bonding later, or VSEPR geometry later. But the key here is beryllium. Some of these bonds that we've considered typically ionic because it's a metal versus a non-metal sometimes can have more covalent character because it's actually a spectrum of bonding between a full ionic and a full covalent bond. Boron, we're going to use boron as a Lewis acid. Don't worry if you don't know what that means. We'll figure this out later. It forms 3 bonds. It is also an exception to the octet rule. It also forms electron deficient species. So basically a boron will have 3 bonds around it, 6 electrons total. And that is normal for boron. That is not something that we have to worry about. Next, we come up with carbon. Carbon will form 4 bonds. These bonds, this definitely obeys the octet rule. I can form single, double, and triple bonds with carbon. So you're going to see carbon that looks like this with 4 single bonds. You're going to see carbon that has a double bond and 2 singles. You're going to see carbon that has 2 double bonds with that carbon in the middle. You're going to see carbons that have a triple bond and a single bond on the other side. Notice I always have 4 bonds with carbon because I have 4 valence electrons Each one of those dots needs another dot in order to form an octet. So carbon is forming 4 bonds. This is one of the reasons why carbon is the central atom in organic chemistry, because it has a very high bonding capacity. It bonds with a lot of different elements in very unique ways, which creates a lot of molecular diversity, which is what we have when we consider biochemistry or other organic chemical fields. Nitrogen has 5 valence electrons. It'll form 3 bonds, and it has 1 lone pair, right? This can also form single, double, and triple bonds. So my nitrogen has a lone pair with 3 bonds. My nitrogen can have a lone pair with a double and a single, or my nitrogen can have a lone pair with a triple. In all of those cases, nitrogen has 8 valence electrons. It has a full octet. And the normal bonding pattern here for nitrogen is going to be 3 bonds with 1 lone pair. Oxygen, 6 valence electrons. It likes to form 2 bonds, and it has 2 lone pair. Right? It'll form single and double bonds. Oxygen will not form a triple bond unless it is charged, and we'll talk about that later. So what you're going to see is oxygen with the 2 lone pairs and 2 bonds, or oxygen with the 2 lone pairs and a double bond. Those are the types of configurations of bonding arrays that you're going to see. I don't like how that looks. Since I'm a perfectionist, I have to change it. But you get the idea. And then my halogens, which is exemplified by fluorine, 7 valence electrons. I'm running out of space there. This will form 1 bond. It has 3 lone pair. It usually forms just single bonds. So here are the normal bonding capacities of the elements as I go across the periodic table from row 1 to row 8 using just the S and the P sublevels. Notice anything above row 3 can form an expanded octet, right? When I have charges, I have a different pattern of bonding. So these are all things that you have to consider when you're drawing your basic Lewis structures to begin with. But this is where you start. You look at this. Remember, the valence electrons are the same in a group. So for group 1, I look here. For group 2, for group 3, for group 4, for group 5, for group 6, and for group 7. I'm going to look at these typical normal bonding capacities in order to start with my Lewis structures. So if I follow those, right, group 3A, 3 valence electron forms 3 bonds, like BH3. It's going to be electron deficient. 4A forms 4 bonds. Methane looks like this. 5A forms 5 bonds, or 5A has 5 valence electrons. It has 3 bonds and 1 lone pair. So when I look at nitrogen and I make this formula, that's ammonia. If I have 6A like oxygen, I have 2 bonds, 2 lone pair, like in water, where I have this guy. HF, right? I form 1 bond, but fluorine still has 3 lone pair. Neon doesn't form any bonds, so that's just the atom that has those 8 valence electrons, and it doesn't form a bond because it already has an octet. These are the things that you have to consider when you put these structures together. And we're going to be doing a lot of this because we are going to look at structure more than anything. We're not just looking at molecular formulas anymore. We're going to look at the structural formula, because we're going to see that because carbon bonds in so many different ways, I could have the same molecular formula and I could have a lot of different bonding types within a molecule. So we definitely have to know how to derive Lewis dot structures. Here, my octet rule is applying to the S block and the P block. Recognize anything in row 3 here can accommodate more bonded electrons. That's called an expanded octet. And hopefully you've talked about that when you actually talked about Lewis bonding in your prerequisite class. So let's practice using this connect the dot structure. If I look at water, I have hydrogens, and I have oxygen. I have 1 electron, 6 electrons, so I have a total of 8 electrons. I'm going to start by putting the electron that has, or the atom that has the highest bonding capacity in the middle. That's oxygen, because it forms 2 bonds and has 2 lone pairs. I'm going to surround it with the other atoms. Literally, I'm going to connect the dots. There I have the Lewis structure for water. If I look at H2CO, I have 2 hydrogens. I have a carbon which has 4 electrons, and I have an oxygen that has 6. I'm going to put carbon in the middle because it has the highest bonding capacity. I'm going to put hydrogens on the other side, and I'm going to put oxygen on the other side of the carbon. I'm going to connect the dots and realize I still have these 2 electrons. Well, I can put those into a double bond in order to give oxygen and the carbon an octet. At this point, I just have 7. Both the carbon and the oxygen needs 8. So if I do that, what I'm going to get is this structure. And let's check my bonding patterns. Carbon has 8 electrons, 2, 4, 6, 8. Oxygen has 8 electrons, 2, 4, 6, 8. Carbon has 4 bonds, right? 2 single bonds and a double bond. Oxygen has 2 bonds, 2 lone pair. I have no charges, so this makes sense. Everything fits. This is going to be the Lewis structure for this particular molecule. If I look at CH4, I have a carbon that has 4. I have a hydrogen, a 3rd hydrogen, and a 4th hydrogen. My central atom is going to be the one that can form the most bonds. I'm going to put my hydrogens around that central atom, and then I'm going to connect the dots, and that's all I have to do, because then carbon has 2, 4, 6, 8, 4 bonds, no lone pairs, no charges. So this is how I recommend that you do Lewis structures. Oops, that's a typo. Here, I have a couple of examples that are from our first chapter in our book. Basically, you need to learn how to read organic formulas. You go left to right. So these hydrogens, because it's CH3, means they're connected to the oxygen. Then I have an OH. This hydrogen is connected to the oxygen. So I'm going to write sort of what I see. I'm going to have 3 hydrogens, and then I'm going to have oxygen, And then I'm going to have a hydrogen down here. So if I actually connect the dots, what I see is I just wrote the Lewis dot structure for methanol. I used the idea that I'm going to read left to right, where these three hydrogens are attached to the carbon is attached to the oxygen, and this hydrogen here is attached to the oxygen, and then I end up with that. I could do this in another way. It doesn't matter if I draw it like this. You could draw it any way you want to, as long as your structure is right. Here, I'm gonna again read left to right. That means these hydrogens are on this carbon. The carbon is connected to this carbon. This oxygen is on that carbon. This oxygen, I'm gonna look at this one because that oxygen is only connected to that central carbon. And then these hydrogens are here. So let's draw the basic structure. I have carbon surrounded by 3 hydrogens. I have carbon. I have an oxygen connected to that carbon. And I have another carbon surrounded by another 3 hydrogens. I'm going to connect all the dots that I can. Do I have an octet? My oxygen up here only has 7, and this carbon only has 7. But notice I have this and this, right? So if I combine those structures into a double bond, what I'm going to get is this. And that is going to be the Lewis dot structure for acetone. So again, you have to learn to read the structure from left to right. Acetic acid, these hydrogens are there. This oxygen are both on this carbon. This hydrogen is on one of the oxygens. So if I actually look there, I have CH3CO2H, right? Again, I'm going to read left to right. I have carbon with 4 dots and 3 hydrogens surrounding it. I have a carbon with 4 dots. I have an oxygen. I have another oxygen. And I have a hydrogen on the end. I'm going to draw all my lines to form my single bonds that just connect 2 dots at a time. And what I'm going to notice is that I have this dot and this dot that can form my double bond. So when I complete this, I'm going to have that Lewis structure for acetic acid. So you're going to notice that we're going to be able to read these different structures, how they're written. You'll get practice with this in chapter 1 homework. If you have any questions, as always, make sure that you talk to me or ask, but that's it for this lecture. And hopefully you guys will remember how to draw Lewis structures after we did all of that material. So keep studying, and I'll see you soon.